Hello dear students, welcome back to Chandu Biology classes, and in this session we will be discussing chemistry of transition elements as well as coordination chemistry. Okay, so this is particularly for IIT JAM BT 2026 and 2027 aspiring students. Okay, I hope you are following our PCM series for your IIT JAM BT and using it very effectively for your upcoming IIT JAM BT exam. Okay, right. So now in this session we will be first discuss what exactly transition elements first. So tell me, see, when it comes to your bio part also, you might be studying about bio inorganic chemistry right now. So along with your biochemistry you might be seeing something like metal complexes. Okay, so metal complexes means, for example, you will be seeing like a hemoglobin and chlorophyll. So what they contains? They contain one metal in the center part, and around that will be having some ligands right now. For example, if you consider hemoglobin, so hemoglobin contains what? Iron at the metal, like iron at the center. So this is a metal, particularly transition metal, around which we will be having 4-5 rings right now. So that is how the hemoglobin will be having. Now here metal, this hemoglobin is one of the example for the metal complexes. Okay, now we need to study or we need to understand this metal complexes. Okay, so before going to that, let me give you some clarity on this transition elements. Like we know in periodic table, yes, I think you know that in periodic table there will be S block elements, and the next here will be having P block elements. Okay, P block elements like this, and here in between them we will be having D block elements right now. So when we are moving from S block to P block, we are like it is nothing but a transition now. So we are it is going like a transition from S block to P block. So in between we have D block elements. So these D block elements are called transition elements. What I am saying, these are called transition elements. Okay, so now these three D block elements, transition elements in the periodic table starts from 4th period. From where it will be starts? 4th period. Let me show you the periodic table first. See, look at this. If you look at this periodic table, so this is first period, this is second period, third period, and our 4th period. From this 4th period, our D block element starts. So atomic number 21, that is for scandium, and goes up to 30, that is for zinc. Okay, it starts from 21 to 30. Okay, and after 31st element again comes for D block. Okay, so how many elements are there in this like in a row here in D block elements? There will be 10 D block elements in each row. Okay, like that you can have 1, 2, 3, 4 rows. In the periodic table we have 4 rows. So the first row starts from 4th period. From where it will be starts? 4th period. So now this will be having 3D series. I mean 3D will be having, like, what is the electronic configuration of scandium? You are saying scandium atomic number 21, right? See, if it is 21, you can write argon. Argon is 18. Okay, after this 18 you will be having 3D and 4s. Okay, so 4s2, 3d1. So 18, 19, 20 and 21. So this will be the electronic configuration of scandium. The next, titanium atomic number is 22. So simply you can remember it is 22 now. So 3d2 you can write, and 4s2 you can write. 22 here 2 and here 2. And vanadium is 23. So vanadium is 23 now. So 4s2, this is s orbital will be 2, maximum 2 electrons only in s orbital. Okay, and the next 23 I am saying now. So 4s2, 3d3, like that. Okay, and for chromium you will be having electronic configuration as 3d5, 4s1, like this. I hope you know little bit about this electronic configuration, right? So now here you know there are when you consider D subshell, what I am saying, like SPDF subshells we are writing now, SPDF subshells we are writing now. So here S subshell contain 1 orbital. How many orbital? 1. And P subshell contains 3 orbitals, like PX, PY, PZ. And D orbitals contain 5. D subshell contain 5 orbitals like this. Okay, similar to that, F orbital contains 7, S subshell contains 7 orbitals. So what are the numbers I told you? S, like S will be 1, P will be 3, D will be 5, and F will be 7, like 1, 3, 5, 7 odd numbers you can remember. So this is the best way to remember number of orbitals in each subshell. So now d orbitals, we are discussing about d block elements now. So why we are saying these are d block elements? Because the last electron of these elements, these yellow color elements, whatever you are seeing, will enters into d orbital, okay. So now what is the general electronic configuration for this d block elements you are writing? So it will be there will be one noble gas here. After this noble gas, you can write n-1d. See, this is 3d you are saying. You are saying fourth period, but 3d series you are using. So n-1d and ns. So there will be ns. It means n I can write 0 to 2 and d 1 to 10. So like this, we will be having a generalized electronic configuration for this all the d block elements. For example, if I want to write for manganese, okay, manganese atomic number is 25. So simply you can write this manganese belongs to 3d series now. So you can write 3d5, 4s2. This is the way you need to write the electronic configuration. First of all, let us understand the writing of this electronic configuration. Then next, everything that is required for you, I mean as per your syllabus, and looking at the questions that are asked in this chapter, from this particular chapter and metal complexes, whatever the questions they have asked, by considering them I have made this session, okay. So I have planned this session as per that only. So just follow the session till the end. Definitely you will be going to get some clarity and confident over this particular over this topic, okay. Definitely it will be, okay, right. First of all, you need to know these 3D series elements, 4D series elements, 5D and 6D series elements, okay. It is better to remember. So what are the elements? Like scandium, titanium, vanadium, chromium, manganese, ferrous, cobalt, nickel, copper, zinc, okay. This one ytterbium, like yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, okay. Now what are the elements belongs to copper family, they may ask. Copper, silver, like copper, silver and Rm, like gold, Au, okay. These are coinage elements also we can say. What is that elements are called? Coinage elements, okay. Now and they may ask what are the chromium family elements. You just remember that as chromo. What is that? Chromo in the short form. Chromium, Mo, MO, okay. W, chromo, I am saying na W, that is what? Tungsten. What is that? Tungsten, okay. So like this you need to remember the elements like a rows as well as like a columns, okay. So how many columns are there here? So 10 columns are there here in total, okay. 10 groups are there in D block, okay. 1, 2, 3, 4, like that you will get 10, okay. So how many rows you are seeing? 4 rows you are seeing for this D block elements, okay, right. Then next, here what are the physical properties and chemical properties? First of all, I am using a word transition elements. What is it? What you are using? Transition elements. So what do we mean by this transition? Okay, see here, whatever the D block elements you are seeing here, these all D block elements can be considered as transition elements, except this last row elements, this last series elements, like this zinc family is there now, that one. Why? Because you can only say transition elements when there will be empty there will be at least some vacancy in this d orbital, at least some vacancy in this d orbital. So when you take a metal of this d block element, either in their metallic state, it means neutral form, or in their most common oxidation state, okay, and in their most common oxidation state, they should have some vacancy in the d orbital. If these d orbitals are completely filled in its free state or in this oxidation, in its stable oxidation state, if there is no vacancy, then you can call them as non-transition elements. For example, what is the electronic configuration of zinc? So its atomic number is 30. First of all, write its atomic number 30. So you are going to get this as 3d10 4s2, okay. So now in its atomic form, it will be having elemental form like 3d10 4s2, and its most stable oxidation state exhibited by zinc is +2, that is zinc +2. Here also it is having 3d10 electronic configuration only, and 4s 0. You need to remove electrons from this outermost shell. 4s 0. It means there is no unpaired electron or there is no vacancy in the d orbitals now, either in their free state or in their oxidation state also. So it means you cannot call this zinc family as a transition elements. Remaining all other elements can be called as transition, but except this zinc family, because they are not showing any vacancy in d orbital either in their free state or in their combined like stable oxidation states. Okay, so these are non-transition elements and other are transition elements, remember this. But we are studying the chemistry of this non-transition elements along with these transition elements only because they are having d orbitals, I mean d orbital electrons, no? That's why. Okay, like last electrons enter into the d orbital only, that's why we are studying along with our transition elements, that's it. Okay, now what are the physical properties you will be having for transition elements? Okay, let me check whether voice is clear, everything is clear. Yes, right. So now here, what are the physical properties here? See, all transition elements display a typical metallic property. What they have? Metallic property. They will exhibit metallic properties, like they have high tensile strength. Okay, so if you apply some stress on a particular transition element, it will withhold, or it has a capacity to hold too much stress on it right now. So that is nothing but tensile strength. Okay, and the next, it has high thermal and electrical conductivity, right? Next, it has malleability and ductility properties, like it has metallic luster also, and it will be very hard, like transition metals are very hard and volatile. Okay, next, they show high melting and boiling points because these are metals which are non-volatile and have high melting and boiling point. Now, what will be the reason for their high melting points and boiling points? See, especially for melting points, due to presence of unpaired electrons, due to presence of high number of unpaired electrons. See, if I write for iron, what is the electronic configuration? Atomic number is 26. You will be writing as 3d6 4s2 electronic configuration. See, like d orbital is having like 4 unpaired electrons here. So these 4 unpaired, due to the presence of more number of unpaired electrons, these transition elements will be having higher melting point. Okay, so melting point mainly it is because of more number of unpaired electrons availability, and next thing is their lattice structures. Okay, these are the two reasons for their high melting points. Okay, and when it comes to boiling point, due to their high atomization energy, what I am saying, atomization energy, they have more boiling point. So what do we mean by atomization energy? See, if I take like atoms here, I mean iron, I am taking iron like Fe. So if this is an iron and this is one more iron, like this, like iron atoms will be like adjusted in the lattice right now. So now due to the presence of more number of unpaired electrons in these atoms, in these transition elements, so more the unpaired electrons, more will be the metallic bonding. Okay, so metallic bonding will be more. Okay, so in order to separate these atoms, see, these are in the lattice structures now. So atomization means we need to separate them like an atoms. So in order to separate them, we need to supply more amount of energy. Okay, because more number of unpaired electrons, more stronger will be the metallic bonding. Okay, so here more metallic bonding now, so we need to separate more energy to separate them. Okay, so more energy is nothing but more temperature now, that is nothing but more boiling point they has. Okay, so due to high atomization energy, they have more boiling point. Okay, right, these are the things you need to remember. Okay, and the next, I hope you are clear with what exactly malleability, ductility and all. See, malleability means what? It is the ability of metals to undergo like a sheets, to form like a sheets. So when we are applying some stress on it, how it will be converting, like it will be converts into thin sheets now. So that is what here malleability we are saying. Next, what about ductility means? They can be like metals can be like we can convert them into thin wires also. See, we can convert them into thin wires, that is nothing but property called ductility. Okay, so now they have lustrous, metals have lustrousness right now. So this is also property of transition elements, and these are non-volatile. Metals are what? These transition elements are non-volatile, remember this point. Okay, and the next here, atomic radii, one of the very important physical property to be remembered. Okay, so now what are the elements we have seen? Scandium, titanium, vanadium, chromium, manganese, ferrous, cobalt, nickel, copper, zinc, like this we have seen. Okay, from 21 to 30, this is 3D series elements. Now what happens is, whenever in the periodic table, when we are moving from left hand side to right hand side, okay, left to right, atomic radius decreases. What I am saying? Atomic radius decreases. So it means scandium, zinc will be like titanium will be having more atomic radius when we compare with these elements. Okay, and one more thing here, one more factor you need to remember. See, what is the electronic configuration here? You will be having like 3D, like scandium, if I want to write 3D1, 4s2 will be writing. Okay, like this it becomes 3D2, 3D3, 3D5, 3D5 again, 3D6, like that. And finally if we come over here, copper and zinc, you will be having 3D10, 4s1, and this one zinc with 3D10, 4s2, right now. So due to presence of completely filled d orbital electrons in copper and zinc, that 3 orbital electrons, see if this is the nucleus, around we have electrons like this right now. So now what happens due to the presence of inner d electrons? See, if I say this is 3d orbital and if I say this is 4s orbital, okay, in which here we have 2 electrons, in here we have 10 electrons. Due to more number of electrons here, there will be repulsive interactions between these d orbitals. Okay, d orbital electron, because fully filled now, this is 10, this is 2. So due to that electronic repulsions, to avoid that electronic repulsions, orbital will expand. So which one? This radius will be expanded to avoid repulsion, in which case in zinc and copper. So from scandium to nickel, up to nickel, radius decreases, but when it comes to copper and zinc, due to more number of electrons, that electronic repulsions will be arises. Due to to avoid that electronic repulsions, orbitals will be expanded. Therefore copper and zinc will be having greater atomic radius when we compare with this. Okay, now the overall order will be something like this: scandium first, next titanium, next vanadium, then next titanium, vanadium, and here titanium, next zinc here, and then next vanadium, next copper, next chromium, like this. Finalized order will be here I have given. First one is which one? Scandium, titanium, vanadium, like this it is going. So from manganese to nickel it will be same. Okay, after this you have zinc is greater than copper. So what is the finalized order here I am writing? Scandium, titanium, and then next zinc, next vanadium, next copper, next chromium, next manganese, and here all the elements manganese, ferrous, cobalt, nickel will be having similar size. So this will be the finalized order for this 3D series. Okay, you need to remember. So what is the reasons we have seen here? So due to repulsions in copper and zinc, repulsions on dominates, then attraction between nd electrons, like n-1 3d electrons, that is what 3d electrons. So due to that reason, zinc is having more size and copper is having more size than this nickel and elements. Okay, whereas this manganese to copper, what we are saying, due to poor shielding of d electrons, attractions increases more than the repulsion, therefore size decreases from here to here. Okay, remember, from here to here. Okay, this is a finalized order, you need to remember. You can expect a question from here. Okay, that's it. Okay, the next one is what happens to atomic radius when we move down the group. When we go down the group, how this atomic radius changes. Okay, it is very easy. So what are the elements? Like we have seen copper, scandium, like titanium this side, here you are seeing like zirconium, yttrium, zirconium, like this now. Okay, so if you see this periodic table, if you see this periodic table, here you have scandium, yttrium, zirconium, yttrium, lanthanum, this downside. Okay, these three elements. Okay, so here you will be seeing the involvement of lanthanides here. What I am saying, involvement of lanthanides. So after this we have lanthanides in between here. Okay, so from here we have lanthanides. So due to the presence of lanthanides, we will be having a concept called lanthanide contraction. Okay, due to that reason titanium, zirconium, hafnium, if we compare, so where this titanium comes, first scandium, next titanium, after titanium here you have zirconium, here you have yttrium, and the next lanthanum, and here you have hafnium. Okay, so between these we have 14 F block elements. Which elements I am saying? 14 F block elements will be involved. Okay, after lanthanum you have 14 F block elements. So before writing hafnium we will be having 14 F block elements. Due to this F orbital involvement, so these side elements, not the scandium family, this side from titanium, zirconium, hafnium, and this what are the elements we are seeing, they will be having some effect of this F orbital electrons, that is called lanthanoid contraction. When it is having lanthanide contractions, and below group will be having actinide contraction. Okay, I will explain what is this lanthanide and hafniide, like lanthanide and actinide contraction. See, so titanium, zirconium, see down the group what happens to atomic radius? Atomic radius should increase right now, but due to the presence of this lanthanides, so when I compare titanium to zirconium, there is little increment in the size, that is fine, but when I go from zirconium to hafnium, the size will remains almost same. Almost same. Look at the values from here to here, increment is there in the atomic radius. Down the group atomic radius increases, we know that is the general factor, but from zirconium to hafnium if we see, size is slightly decreasing or almost becoming same. So what is the reason? That reason is called lanthanide contraction. What exactly lanthanide contraction? See, if this is a nucleus, we have s orbital and we have like p orbitals also we can have d orbitals and we can have f orbitals. Like this we have like s, p, d, f orbitals are there. So but s orbital is spherical, p orbital is dumbbell shape, and d orbital is double dumbbell shape like this, and f orbital is like complex shape. Okay, so now if you observe this, look at the structures of the shapes of this SPDF orbitals, like s orbital is more symmetric around the nucleus, therefore it will be protect the outermost electrons very effectively. Okay, but when it comes to f orbital, see, it will not be symmetric as like s and p orbitals. It is very less symmetric. S orbital and d orbitals are very less symmetric. When it comes to f orbital, like when it comes to f orbital, it will be having very less symmetric nature. Okay, so if it is very less symmetric, what happens? The nucleus can show its positive nature up to the valence shell electrons. If it is showing up to the valence shell electrons, whatever the valence electrons are there, those will be strongly attracted towards the nucleus. Therefore what happens to the size? Size will decreases. Okay, size of that elements decreases. So this is called poor shielding of f orbital or lanthanide contraction. So due to the improper shielding of f orbital, the nuclear forces acts up to nth level electrons and drags the nth level electrons more close towards the nucleus. That results to decrease in the size. Okay, so this concept is called lanthanide contraction. Okay, so due to the lanthanide contraction only, zirconium to hafnium, the sizes are almost being equal. Okay, due to this involvement of 4f electrons. Okay, this is the concept involved here, right? If the discussion is clear, just mention clear in the chat box, or you just click on the like button, that's it. Okay, right, let me give you some questions. Definitely you are going to get full confidence once after ending up this session on this inner transition elements as well as coordination complexes. Okay, just be patient and listen to the class. Right, yeah, so this is about size or radius changes. Now you know oxidation states, like you know this transition elements shows a different oxidation state. What I am saying, due to the presence of different number of d orbital electrons. What is the valence electronic configuration we have written? Like for 3d orbitals, if I say 3d series, 3d 1 to 10 you have seen, 4s 1 to 2 you have seen for all 3d series elements. Right now like it can now lose this s orbital electron as well as some electrons from this d orbital. Okay, therefore you are going to get a different number of possible oxidation states for different elements. Okay, so now in different oxidation state this element can show different colors. For example, here let me show you one simple way to understand. See, if you observe the 3D series element, scandium, titanium, vanadium. See, vanadium has electronic configuration 23 now, so you are writing it as 3d3 4s2. So now how many valency electrons are there? Here after argon you have 5 valency electrons. Okay, now vanadium can lose 2 electrons from this s orbital and can exist as argon 3d3. Okay, or it can also lose all these 3 electrons also, and now it becomes argon 18, that is 18 3d0 4s0. So this is also possible. So when it is existing like this, you can say vanadium is in +2 oxidation state. Here all the electrons are removed now, you can say +5 oxidation state in this case. Okay, like this different oxidation states are possible for the 3D series elements. Along likewise we can also have for 4D and 5D series elements also. See now, what are the elements exhibits +1 oxidation state in 3D series? See, you have only one copper atom here, because what is the electronic configuration of copper? You can write 3d10 4s1. Okay, like 29 atomic number for copper, so it will exhibit 3d10 4s1. So now it can lose this 4s1 electron and can stays as copper +1 having electronic configuration 3d10 4s0. Now fully filled electronic configuration is stable now, so exhibit +1 oxidation state, unipositive. Okay, remember, so which one? Copper only. Okay, the species in half filled and completely filled electronic configuration exhibits more stability. That's why the +1 oxidation state of copper is more stable, as well as zinc can also show 3d10 electronic configuration in their +2 oxidation state. Just remove 4s electrons and zinc will exhibit in +2 oxidation state. Okay, and you know, when it comes to manganese, now what is the electronic configuration of manganese? You can have 3d5 4s2. So you can remove these 2 electrons from the manganese and you can exhibit +2 with d5 half filled electronic configuration, or you can remove the d block elements electrons also, like d orbital electrons also. So it can exhibit from +2 to up to +7. See, total number of electrons possible here how many? 7 electrons are there in the valency of manganese. So we can remove all the 7 electrons. So the maximum oxidation state shown by manganese is +7. What is the maximum oxidation state shown by the manganese? +7. Okay, so what are the possible oxidation states for manganese? From +2 to +7, all oxidation states are possible for manganese. Remember this. So now one more statement they will mention like this. What is the maximum oxidation state shown by 3D series elements? So for 3D series elements, the +7 will be the maximum oxidation state, and that is possible for manganese. And iron can show maximum of +6 oxidation state only. Remember this point. Okay, right. Alright, next, so in complete D block elements, what is the maximum oxidation state possible, they may ask. So the maximum oxidation state is possible is +8, that is by osmium. What is that? Osmium. Okay, remember this. Osmium can show +8 oxidation state also. Remember this very, very important points. Okay, the next thing is here is, now we know manganese can exhibit different oxidation state possible from +2 to +7 we discussed. Okay, so now you know manganese in +2 it will be colorless. When it comes to +6 it will be having green color. Okay, what is the color? Green color. And you know this different oxidation state, different color nature we are seeing now. So now what is the responsible or what is the reason for their colors? This is a very, very important question. We have 2 questions under color property. I will show you from the PYQs. Okay, so the reason for the color of D block elements is one is DD transition. What I am saying? DD transition. And one more reason is charge transfer phenomena. What is the one more reason? Charge transfer phenomena. And third reason is polarization. So these are the three reasons for color property of D block elements. Okay, remember. Okay, so now let us understand what exactly DD transition, charge transfer phenomena, and this polarization. Let me explain. Let me explain this. See here, different oxidation states for the different elements and different colors. You need to remember these colors also. We have a question on this. Now I will show you. Okay, before that, let me explain about this color property. For example, you take any metal here. For example, Fe plus 3 is there. So it will be having no d5 electronic configuration. You know, these d orbitals will split into two energy states, like lower energy T2G set, higher energy EG set, or in the reverse manner depending upon the type of compound it is forming. Okay, finally what I am saying, there will be two energy levels, like different energy levels for these d orbitals. Okay, now what happens, electron from lower energy state, whether whatever may be the electronic configuration, but if it is having any d electronic configuration from D1 to D9, what I am saying, D1 to D9, then electron can go from its lower energy state to higher energy state. Okay, when it is going from lower energy state to higher energy state, it requires some energy now. That required energy absorbed from the visible region. What I am saying, it will absorb from the visible region, and electron will excites to higher energy state. Now during this process it is absorbed some energy now. Okay, and electron may come down to the ground state again, come back to its original state. So now this absorbed energy and that emitted energy will fall into the visible region only. If it is fall into the visible region, definitely we will be having some color emission. No? So now always remember, if it absorbs higher wavelength, it will emit lower wavelength. It means if it absorbs high energy light, it will emit low energy light. Like absorption spectrum and emission spectrum will be complementary to each other. Something like if we say like VIBGYOR colors, like visible region, VIBGYOR colors, if you take this VIBGYOR colors, if it is absorbing like you know, from moving from here to here, red color will be having lambda maximum. Okay, maximum lambda, low energy. What I am saying, low frequency and energy. This will be having maximum frequency and energy. I hope you know this. And minimum lambda for this VIBGYOR. Okay, violet color. Okay, so now if it is absorbing something like violet color, it might emit this orange color. Okay, if it is observing this blue color, something like yellow will be emitted. Like this, we will be seeing the colors for these d block elements. So what is the reason? The reason is simple. Electron transition from lower d orbital to higher d orbital. That is nothing but d transition. D orbital to d orbital electron transition is responsible for color. But what I have mentioned here, 1 to 9 I have mentioned here. Okay, so this 1 to 9 is perfect. Sometimes metals may be in 0 oxidation state, sometimes may be D10 oxidation state. So in these cases, this DD transition is not at all possible because there is no d electron only in this case. Therefore, if no d electron, no DD transition. And here D10 means all the d orbitals are completely filled now. So if it is completely filled, that means there is no possibility for electron excitation because all these shells, all these orbitals are filled. So that means there is no DD electronic transition in these both cases. Now here the color may not be due to DD transition, but there is some other reason like charge transfer phenomena, or it might be polarization. Okay, now you need to understand what is charge transfer phenomena. Okay, before understanding that, just look at this. What are the colors? Titanium plus 3 means it is purple. Okay, chromium plus 3 means green. Okay, manganese plus 2 pale pink. Okay, a light pink. Ferric Fe plus 3 means Fe plus 3 is yellow, and cobalt plus 2 is pink. Okay, cobalt plus 2 is pink, and nickel is plus 2 is green, copper plus 2 is blue. So why I am saying this? Just look at this question. They are asking. See here, I told you one simple trick to identify. What about zinc? It is having 3d10 electronic configuration now. So 3d10 means there is no dd transition. If there is no dd transition, no color. Okay, it means zinc plus 2 does not show any color. So Q1. Okay, after this Q1, and after this cobalt plus 2. What is the color we discussed just now? It is pink now. Just look at here, cobalt plus 2, pink. That's it. Cobalt plus 2 is pink. So P3. So P3 in option 1, Q1 in option 1, P3 in option 3, Q4. No, not this one. So your first option is perfectly correct, because P3, Q1 and R2, copper plus 2 is blue. Okay, copper plus 2 is blue. Yes, perfectly correct. And nickel plus 2 is green. That's it. That's it. So this is from the previous table. You can able to answer this question. Hope the discussion is clear. How simple question is, just you need to remember this table. Okay, these colors are important. Okay, and what is the reason? dd transition is one reason, and the next thing is charge transfer phenomena, one of the very important concept. For example, you know KMNO4, that is potassium permanganate. You might be seeing it from many days in your lab, like BSc laboratory or your intermediate. From your intermediate onwards, you might be seeing this KMNO4 right now. BSc, MSc laboratories. See, what is the oxidation state of this manganese here? +7. If it is +7, what is this electronic configuration? Normally atomic form 3d5 4s2, but it is in +7 now. It becomes 3d0 4s0 right now. So 3d0 4s0. Now there is no electron to show dd transition, but it is having some purple color right now. KMNO4 will be having purple color. So what will be the reason for this? See, it is having +7 electronic +7 oxidation state, and here oxygen is in oxide form, O-2 form. So you can call it as oxide. What is this? Oxide. So we know definitely potassium will be +1 oxidation state in any of its combined forms. Okay. Now what happens is, due to availability of this vacant d orbital here and availability of more electron density on this ligand, what I am saying, like ligand here. Okay. So this oxide will donate electrons or donate charge to the empty orbital of this manganese. So it is nothing but charge is transferring from ligand to metal now. So what is the responsibility? The charge transfer from ligand to metal. So charge transfer to ligand to metal. So ligand to LM, ligand to metal charge transfer. This is responsible for color of this KMNO4, and this, due to this charge transfer, the intensity of color is more. The charge transfer color will be very intense color. Okay, remember. Okay, now look at the question asked on this. Okay, let me show you some question asked from here. Let me check it. See here, the deep pink color of aqueous KMNO4 solution is due to, what is the reason? What might be the reason? So tell me, anyone in the chat box, what will be the reason for this deep pink color? Yes, you can easily answer. Just now I told you, there will be a charge transfer from oxygen to metal. Right now, oxygen to metal, like oxide to this manganese +7. Okay, so you can say a strong ligand to metal charge transfer is taking place. So this will be a perfect answer for the question. Remaining, there is no dd transition here, that is not responsible, and there is no charge transfer. See, in some cases from metal to ligand also charge transfer takes place. In which cases, if metal has more electron density and ligand has some vacancy either in their orbitals or in their pi star antibonding orbitals at least. So I can say pi acidic ligands if we have, then there is a chance for transferring electron from metal to ligand. So in that case we can have MLCT also. So now, but in this particular KMNO4 case, what is the reason? That is LMCT, ligand to metal charge transfer. Okay, ligand to metal charge transfer. Remember this. Okay, right. Next, same story applicable for K2Cr2O7 also. K2Cr2O7, which is having orange color now. What is the reason for its orange color? It is just a charge transfer from ligand to metal charge transfer. Ligand to metal charge transfer. Remember these two examples. And then next, see here we have a question on dichromate and chromate. See, chromate, yellow color of chromate. See what is they are saying? Cr2O4 minus 2 is yellow color. So chromate is easily converted to orange color by any acid. This transformation is, see, so now this will be converted into K2, I mean Cr2O7 2 minus they are saying. So this conversion is in presence of acid takes place, they are saying. Okay. So now this transformation yellow chromate is easily converted into orange dichromate by an acid. Okay. So this transformation, see how many we have here? 2 chromate ions are there. So you can get a dichromate. This is nothing but a dimerization now. So what is happening here? Dimerization is taking place. Okay. What is happening here? You can say dimerization is taking place. But one more thing you need to remember here. First option will be perfect. So one more thing you need to remember here is, see here it is plus 6, there also it is plus 6 oxidation state only. And you know this is yellow color, this is orange color. So now we can make one more statement here. See, so this will be in equilibrium at pH 4. What I am saying, this will be in equilibrium at pH 4. If you add more quantity of acid, equilibrium shift forward. It means orange color will be intensified. Okay. If I add basic medium, then equilibrium goes backward. Yellow color will be more intensified. Okay. Remember the acidic medium and basic medium, that how that will be impacting on the intensity of colors. If acidic medium, more orange color. If basic medium, more yellow color. Okay. Remember these 2 points. Okay, I hope it is clear that the discussion on the color property and all. Now we need to understand. Now we need to understand the metal complexes. First of all, what exactly metal complexes here? Metal complexes. See, just now you have seen metal complexes. Here transition metals are there. Transition metals means what? Any of this 3D series, 4D series, 5D series, in which exceptional case is that zinc family. Okay, so you take any iron plus 2 or any of this ion. So now if I compare this iron plus 2 in its normal existence, and when it is forming a complex with the same Fe plus 2 oxidation state, always remember metal complexes are more stable than its free ions. Okay, that's why the free ions combine with some ligands and form metal complexes. Okay, so what I am saying, transition metals are more stable in their complex states when we compare with their free metal ion states. Okay, remember this. Next one, so whenever a complex is forming, generally complexes are represented in this manner. Okay, I hope you know there are many applications for these metal complexes. See, cisplatin we are using for cancer therapy. I think you know about this, and also we'll be having many other catalysts also, like Wilkinson catalyst I am saying. So what is this Wilkinson catalyst? It will be used in the chemical reactions, like RH, PPH3, Cl will be using as a catalyst. So it has many different applications in our chemistry as well as chemical synthesis and medicinal chemistry and also other industries. Okay, right. Let me show you a metal atom will be there. There will be some ligands. Okay, what is this ligand means? These are the more electron density containing species which donate electrons to this central metal atom or ion. Okay, so general construction you can make Ml will be there with n number of these ligands. Okay, and it might be having some charges sometimes. So I am indicating here some plus X charge, plus or minus it may be. Okay, right. So now M is a central metal atom in this complex. A complex will be represented within the square bracket. Okay, so the best example here I want to represent is cobalt hexaamine chloride. So what it is showing here, what is the central metal atom here? Cobalt. And like we have ammonias now here. So how many ammonias are there? 6 ammonias are there. So each ammonia having lone pair will be donated into the empty orbital of this cobalt. Okay, like that, how many ammonias are there? 6. So 6 ammonias are now called as 6 ligands. Okay, what I am saying? 6 ligands. So outside the coordination sphere, this square bracket is called coordination sphere or coordination entity, and this outside we have now, so this is called ionic sphere. Okay, what I am saying? Ionic sphere, particularly anionic sphere. Why anionic sphere I am saying? For example, whenever you are writing sodium chloride, how you will be writing? First cation followed by anion. So now in the cationic position we have our metal complex ion. Okay, and in the anionic position we have this chloride ions right now. So now we know halogens are with negative charge, like that will be in chloride form, minus. How many are there? 3 are there. Okay, so 3 chloride ions. So if you remove these 3 minus charges, our complex should get a positive 3. So plus 3 oxidation state on it. Okay, right. And you know ammonia will be a neutral ligand, like it will not be having any charge on it now, it will be having simply this lone pair electrons is donated to our cobalt. So therefore 6 ligands are there, the charge with respect to each ligand is 0. Now what will be the oxidation state of this cobalt here? Consider X is the oxidation state of cobalt, and there are 6 ammonia ligands, each ammonia ligand is neutral, so 6 into 0, which is equals to, now what about the charge here? Plus 3. How this plus 3 is coming? When we remove these 3 chloride ions, there will be charge of plus 3. So now what is the oxidation state of cobalt in this case? Plus 3. That's it. This is the oxidation state of cobalt. If it is cobalt is in plus 3 oxidation state, what is the electronic configuration it becomes? See, in its neutral state, cobalt atomic number is 27. So you are writing it as 3D7, 4s2 you are writing 27 now. So S2D7. Okay, remove 3 electrons from here. So 2 from here and 1 from here. So it becomes 3D6, 4s, 0 electronic configuration for cobalt plus 3. Okay, in this complex this is the electronic configuration you need to remember. Okay, and we know you know there are 2 terms we will be using here. One is oxidation state, another one is coordination number. What do we mean by coordination number? Number of ligands around the central metal atom is called its coordination number. Okay, for example, here I am writing a ligand here, just to see CH2, CH2, NH2, and here also I am writing NH2. Okay, see, we know this nitrogen of ammonia, like amine will be having lone pair, so that can be donated to a metal central metal atom, and from this side also it can be donated right now. So now I can say if a particular ligand is having more than one dentating site, like here we have 2 dentating sites, so you can call this as bidentate ligand. If it is having 3 dentating sites, tridentate ligand, 4 tetradentate, 5 pentadentate, 6 hexadentate. For hexadentate we have a very best example, that is EDTA. So ethylene diamine tetraacetate. Okay, so it will be in the -4 state, act as hexadentate ligand. What I am saying? Hexadentate ligand. Okay, now you know we are simply covering, I mean I just want to cover everything but in a very simple manner. See, because you have lot of syllabus, your bio syllabus is almost too much. Again, along with this chemistry also, if you want to cover complete BSc syllabus in detail, you might feel too much nervous and will be very stressed right now. So what I am doing, I will be just picking out the best topics, I mean very important topics that must be focused for your exams. Okay, that's why I am covering as much as simple possible. Okay, so now here EDTA can act as hexadentate ligand when it is in -4 oxidation state. Remember this point. Again, so how many dentating sites are there? 2. So I can say this is a bidentate ligand. Okay, so now how many dentations? This side 1, this side 1. So now if I ask what is the coordination number of this metal with respect to this ligand, means you should say 2, this side 1, this side 1. Like this, the what is again, what is the name of this ligand here? I can say ethylene. What you can say? ethylene diamines. So ethylene diamine, in the short form we can represent it as ene. What is that? Ene. Ene represents ethylene diamine. Okay. Now how do you write? Let me give you one example. Cobalt, ene twice, NH3 twice, chlorides. Like this they will mention, and they will ask what is the oxidation state of this cobalt and coordination number of this cobalt. This is a question they will mention. So can you answer me this one? So what will be the answer for this? See, first of all, oxidation state. Ethylene diamine is a neutral one, as well as ammonia is also neutral one. So therefore, inside there is no charge, but outside you have chlorides now. So you just take X for this. So for this will be 2 into 0 plus that is also 2 into 0 plus here 3 chlorides are there now, 3 into each chlorine will be minus 1 form. So minus 1 equals to overall charge is neutral. So take it 0. So oxidation state here also plus 3. Like this you need to calculate the oxidation state. You got oxidation state. Now one more question is coordination number. So how do you find these? Let us make one generalized formula. See, ligands can be monodentate, ligands can be bidentate, tridentate, polydentate, like that now. So coordination number will be equals to 2 into, like if there is only monodentate ligand, so 1 into monodentate means only one side dentation. So 1 into number of monodentate ligands, ligands plus here some bidentates also there. So bidentate means there will be 2 dentating sides now. So 2 into number of bidentate ligands. And if there is tridentate, it means 3 dentating sides, 3 into number of tridentate ligands. If there is 4, then 4 into tetradentate, then 4 into number of tetradentate ligand. Like that you can use the formula. So now based on this, tell me what will be the coordination number for this particular complex. Coordination number will be equals to, so there is 2 monodentate ligands, 2 into each like see, 1 into number of monodentate ligand, 1 into number of monodentate ligands are 2 plus bidentate ligands are 2, so number of bidentate ligands are 2 and what is its denticity? 2. Therefore tridentates nowhere. Okay, so here 2 2 is 4 plus 2 6. What is the coordination number of this cobalt in this case? 6. Oxidation state is plus 3. Okay, this is very very important. Okay, and one last point I want to add here is, these oxidation states are also called as primary valency. What I am saying? Primary valency. Whereas coordination number is called secondary valency as per Werner's theory. What I am saying? Werner's theory. So when we say oxidation state, that is also called as ionizable valency or primary valency. Coordination number is called secondary valency as well as non-ionizable valency. Remember these two terms, and questions regarding that I am going to give in the upcoming sessions. Okay, right. So now they will ask something like this: what is the spin only magnetic moment for this particular complex? See, there are many questions asking about magnetic nature, see, and they are asking what is the name. So in order to write its name, you need to know its oxidation state that must be represented. We will be discussing everything related to these particular complexes and questions. See, this many questions are waiting for you, and you just need to join our next session on this particular discussion of metal complexes, and I am going to discuss their IUPAC nomenclature as well as what are the ways that we can explain this metal complex. That is nothing but theories in coordination complexes. We will be discussing where we are going to cover all these questions. Okay, right. So this is for you only. Just come join and make your preparation more effective. Okay, so thanks for watching. Stay connected with these Chandu biology classes and make your preparation more effective and more productive. Thanks for watching.